Good afternoon. This is our 719 Mathematical Economics. And today we're going to continue with our study of dynamic programming problems. Let me share my screen. Okay, so let's minimize that. So last week we looked at the guess and verify method. Okay, so today's task is to look at what we call value function iteration and policy function iteration. To be specific, so these are projection methods or projection-based methods. So most of the time you use a computer. You use a computer to do that. In value function iteration, we want to approximate this function, the value function. In policy function iteration, we want to approximate these functions. Remember, our simple problem was expressed in this way. So there was this logarithmic utility. Then we have the continuation value. Then there is the constraint, right? The constraint is lambda kt alpha greater than or equal to ct plus kt plus 1. Okay, so here a solution, of course, is described by these policy functions. Okay. And if you recall, so this equation, the Bellman equation, is a functional equation, right? So if you rewrite it in this way, Vk equals, so imagine that you solve the problem. So you have natural logarithm of ck, right? Plus beta v. Then you have lambda k alpha minus ck, right? So if you really solve the problem by this policy function, then this equation is a functional equation in two unknowns, unfortunately, right? So if we know ck, if we know the policy function, we can find value function. If we know the value function, we can find the policy function, but we cannot do it both. So that's the idea of using projections, all right, or the guesses, right? So last week we use a guess. If we are lucky, the guess is correct, so we can verify it. That's the solution. Now we're gonna look at projections. So we're gonna project first a value function for the initial. So these are iteration methods. Okay. So we're gonna keep trying to find the correct ones. Okay. So it is an iterative process. In the value function iteration, we start by guessing values for value function, and then we keep iterating the Bellman equation. In the policy function iteration, we guess the policy functions, then we again iterate the Bellman equation, and we want to find ck and kk. Okay. So again, these are numerical methods, because most of the time we use them to study a little bit more difficult problems, right? Because if the problem is very simple, you can always use guess and verify, and sometimes Lagrange would work, right? So you wouldn't really want to deal with the numeric methods, but sometimes the problem is too complex. Okay, and because of the complications, we want to use such numerical procedures to arrive at approximate solutions. Of course, these are going to be approximations. Okay, but I want to show you here first the analytical foundations of these methods, right? Because If you understand the analytical foundations, you can always, okay, there's a typo here. Let me correct this. This may be confusing later on. So this will be, of course, KKT. So once you get how the analytical system works, then you can always code it. You can do it in MATLAB, you can do it in R, you can do it in Python, whatever platform you are using for such things. And actually, you can find other people's codes, so you can use them as well. In that regard, a useful resource is QuantEcon. QuantEcon by Sargent and Stachursky. Sargent and Stachursky. So in this website, they have some lectures. They have the Python and Julia codes. Okay, it's totally free, so you can go there, read the lectures, and you can find things such as value function iteration, pulse function iteration codes. Okay, so let's start with the policy function iteration. Value function iteration. Okay, so the idea is this: we want to write the Bellman equation in this particular way. I want to write the Bellman equation as a mapping. Okay. Remember, I mentioned, and don't forget the constraint. Your constraint is KT alpha equals KT plus 1 plus CT. Okay. So here J denotes our iterations. Okay. And the idea is to do this. So in step 1, we want to start with a value function. Okay, this is for J equals 0, right? We want to start with a value function that is very simple. So what could be the simplest form? What could be the simplest form of the value function? It's very simple, 0. Okay, so for any KT, okay, we start with an initial iterate of no continuation value. Now, if this is correct, if I specify my value function, I can also write this, right? Then this is 0. Now I realize look at this. I realize that part, right? So step 2, find CT that maximize V1 KT, right? Because now the right-hand side is there. So how do I find that? Well, the problem is now very simple. ln CT plus, so I'm maximizing by choosing C ln CT beta times 0, right? And I am choosing CT from this compact set, right? So CT is basically what? Lambda KT alpha. Okay. Now, what does this give me? It gives me V1 KT, right? Because V1 KT is basically ln CT plus beta times V0 KT plus 1, right? And this is already 0. So what is V1 equal to? V1 is equal to natural logarithm of lambda kt alpha. Okay. So what do I learn from at this step? Well, I realized that V1, now I'm realizing that V1 kt is equal to natural logarithm of lambda kt alpha. In other words, it is basically this. Now, you already know the correct solution, right? Now, compare V0 kt equals 0 with V1. What do you see? Even in this first iteration, it is closer to the true value function, right? Even in just one iteration, because this is a very simple model. So what happened? I start with a value function that is completely wrong, right? No continuation value for tomorrow. But then the solution that gives me the wrong solution, obviously, right? Consuming everything, that gives me another value function. Because now you can now start understanding the notion of the contraction mapping, right? Now it will take me to the correct value step by step. Okay, so now I have V1 kt. So I have V1 kt plus 1. This is very simple. I have ln lambda alpha ln kt plus 1. Then I go back to step 2, right? And do the same thing again, because my Bellman equation now can be written in this way. Maximize ln ct beta, careful. So this is now ln lambda plus alpha ln kt plus 1. Okay. Now I have again ct kt plus 1. So if I replace kt plus 1 with lambda kt alpha minus ct, then this is only a problem in terms of ct. So you maximize ln ct plus beta, and then you find ct again. Okay. Oh, by the way, so sorry, I missed step 3, right? So this was yeah. So in step 3, let me use this one. So step 3 is here. You check whether Vj kt is approximately equal to Vj plus 1 kt. Okay. So if you satisfy this constraint, okay, if you satisfy this, then you stop, right? Because it means it already converged. If it is not satisfied, then you go back to step 2 and do this, right? You do this. Then again, you check whether, now here I am checking V0, V1. At the end of this step, now I will have V2, right? Then I will check whether V2 is approximately equal to V1, all right? Then if this is correct, I will stop. If it is not correct, I will go back to step 2. Now I'm gonna use V2, right? To write V3 in this way, right? And I will continue. That's the idea of value function iteration. We are iterating over the Bellman equation, and step by step we get closer to the true value function. Okay. Now, if you think about this a bit more carefully, of course, you are going to do that numerically, right? Then the stopping constraint is something like this. You want to have a distance between 2 iterates. Now this is norm, all right? So this is basically some sort of a distance, okay? But here you have, of course, for each KT, you will have many different values, right? So these are vectors, actually. Then you find this norm. So if this norm is less than epsilon, here epsilon is some very small number, such as 10 to the 8, minus 8, okay? Then you stop. If that is not true, you're gonna continue, okay? You're gonna continue until this norm, this difference is less than some epsilon. And you also, in computer, of course, you cannot write this set in this way, right? You want to stop at some point, but J will be some large number, such as 10,000, okay? So this is the maximum number of iterations. Okay, so let's continue with our analytical example. So, so we had V1 KT equals ln lambda alpha ln KT. So then if you maximize ln CT plus beta ln lambda plus beta alpha ln, now be careful, I'm writing this for KT plus 1, right? So what do I have? I have 1 over CT plus beta alpha minus 1 lambda KT alpha minus CT. So that's going to be equal to 0. So then I have lambda KT alpha CT equals what? Alpha beta CT, right? So CT is going to be equal to 1 over 1 plus alpha beta lambda KT alpha. Okay? Then you have V2. Right? Now you can write V2 in this way. You have natural logarithm of CT. So it is that. Okay? Then you have beta ln lambda. Then you have beta alpha ln KT plus 1. So KT plus 1, as you see, is alpha beta 1 plus alpha beta lambda KT alpha, right? Because a fraction 1 over 1 plus alpha beta goes to consumption, the remaining fraction goes to saving. Okay, now as you realize, this is V2, and now V2 is again a function like this, but parameters are different, right? There will be a bunch of constants, and so these constants will be different than ln lambda and alpha. For instance, you're gonna have alpha here, then you're gonna have alpha square beta from here, right? So you're gonna have alpha plus alpha square beta ln KT, right? Yes, alpha square beta, and you're gonna have alpha from here. Then you're gonna have some other constants here, okay, depending on lambda, alpha, beta. All right, these are the parameters. Then you have V2. Okay, then you're gonna continue. First, you're gonna check, of course, at that step, you realize that this is not correct. Okay? You should realize that this is not correct. So you're gonna do it one more time, one more time, and at that time, you're gonna see the pattern. So there's always a pattern if there's solution, all right? So you have now V2 KT plus 1. It is like a bunch of constants plus alpha square beta ln KT plus 1. Okay, so your V3 is maximize ln CT plus beta, some constants, right? Plus beta alpha square beta ln lambda KT alpha minus CT. So you do it again, 1 over CT now equals beta alpha square beta divided by lambda KT alpha minus CT. So you have beta alpha square beta CT equals lambda KT alpha minus CT. So CT is 1 over 1 plus beta alpha square beta times lambda KT alpha. Okay, and obviously it is also different, right? So it's now changing. So if you give this within the so if you write this explicitly, you will have 1 plus alpha beta plus alpha square beta square. Okay, now you must be seeing the pattern, right? Now there is a pattern. Do you see it? The pattern is at some j equal j, at some very large, if you keep doing that, okay, at some point you're gonna find a consumption function. Okay, so this was iteration 3. So you're gonna find this as 1 over 1 plus alpha beta dot dot dot, so alpha beta square dot 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 alpha beta j minus 1. Okay, and you have lambda KT alpha here. Okay, so what happens if j goes to a very large number? Of course, that's going to be converging, right? Because that's a geometric sum. So that will converge. That will converge. So you write it in this way. So 1 alpha beta square dot 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 alpha beta j minus 1 is written in this way, obviously, right? So so you have j from 0 to j minus 1 j, right? So if j goes to positive infinity, then this sum is going to go to, so this sum is going to go to 1 over 1 minus alpha beta. What's the condition for that? The condition is this is less than 1. Is this less than 1? Yes, because alpha is between 0 and 1, and beta is between 0 and 1. Okay? So analytically, of course, it will take many iterations, right? And it will never stop. But numerically, you're going to stop once the difference is very small. You're going to stop again once this difference sorry, j plus 1 is smaller than your epsilon, okay? So when you are doing this numerically in practice, of course, at some very large j, let's say at 200, okay? Or, I mean, this entirely depends on the model. It takes 2,000 or 20,000 iterations. I don't really know. It depends on the model. But this is the very simple model. After a couple of iterations, the difference gets very, very small. Okay? So in like 5 or 10 iterations, it will get very, very small. So you can actually find the policy function. Sorry, the value function. Okay? And once you get the correct value function, of course, your solution, your policy function is also approximately correct. Okay? So once you now you can check it. So CKT will be lambda KT to the alpha divided by 1 over 1 minus alpha beta. In other words, it will be this. Now, and this is the correct one, right? Because I remember that KT is also alpha beta lambda KT alpha. Okay? So be careful with the difference between analytical solution and the numerical solution. In the case of analytical solution, that iteration continues forever because you can always approximate it. You keep approximating it analytically. Numerically, this tolerance level allows you to stop at some point. Once the difference is very, very small, you don't care about that very small difference. It's good enough, you say, and you're gonna stop. Okay. So let me now stop and respond to your questions if you have any. Anything that is unclear, anything that I can cover again, I can always explain.
Sorry, I couldn't understand exactly the CKT equals to lambda KT alpha. And can you clarify the last part of the question?
All right. So let me share it. So what we realize is this, right? So once we continue with the approach that I just explained, so let's go a couple slides back. So at the first step, I find, all right, well, let me do like this. So at the first step, what I found was this, right? CT equals